Okay, this is the note set for section 4.2 in Math 31. We're going to do two separate videos just to break it up a little bit. And this is part 1. So writing a number as a product of prime numbers with the ultimate goal here of writing fractions in simplest form. So factors are parts of a multiplication problem. And you can see in this first example, I've made a multiplication problem that yields 45. So we would deduce that in both 9 and 5 are factors of 45. There's other ways you could have broken that up, such as 3 times 15. Okay, and you look at 48, and the factors of 48 are 6 and 8, and we're supposed to circle them. So that's one way to break apart 48. You could say 3 times 12 is another way. So let me go back and circle the factors in the other one. Factors are parts of a multiplication problem. And you have learned from these first two examples here that it can be done several ways. Now, except for the 5 in example 1a here, namely that one, all of these examples are themselves numbers that could be broken down. For instance, the 6 that's down here could be 3 times 2. And the 8 could be broken down into 4 times 2. Any number that can be broken down further is called a composite number. So the composite numbers in the examples above are 9, because it can be broken down into 3 times 3. 6 is also composite because it's composed of 2 times 3. 8 is composite because it could be composed of 2 times 4. If a number can't be broken down any further, then it's called prime. And the only way to actually break down 5 is 1 times 5, which really doesn't change anything. It's you're still dealing with a number 5. So the way we define prime numbers is any number that has exactly 2 factors, one of them being the number 1 and the other one some other factor. So prime numbers, it would be like 1 times 7 is the only way to break down 7. So 7 is prime. 13 can only be broken down as 1 times 13. So by definition, it has the factors 1 and 13. And if it has exactly 2 factors, one of them being the number 1, then you are dealing with a prime number. But when you get to the 20, and I'm going to paint that in pink, that's called a composite number because there's a lot of ways besides 1 and 20 you can break down 20. You can probably think of a couple, but one of the examples would be 4 times 5. Okay, the number 1 has only one factor. The number 1, you might go, well, what about 1 times 1? Well, you said 1 twice. And because of that, it kind of disqualifies itself because if you look carefully at the definition, it has to have exactly 2 factors, namely 1 and a different number itself. So 1 is not considered to be prime. Ironically, I think it was earlier in my career. So here's a partial list of the prime numbers. 2, 3, 5. Let me explain why we're skipping 6. 6 is composed of 2 times 3. It's a composite number. 7's in the list of prime numbers, but 8, 9, and 10 are all left off the list. They are not prime. Instead, they're composite. Think of just the 10. Okay, 10 could be broken down. Besides 1 times 10, it could be 2 times 5. 11, 13, 17, 19, 23, 29, 31, and so on, although there's not a real apparent pattern to these. In fact, it's a rather random pattern, and just as an interesting side note, anytime you make an online purchase, the information you encode, your credit card numbers and so forth, is encrypted with very, very, very large prime numbers being used. Okay, so that keeps things supposedly secure, although honestly, some of these systems can be broken with enough computer time. So, show that the following numbers are composite. All you have to do is show that besides 24 being 1 times 24, if you can show any other way of breaking down 24, then you've shown as composite. 2 times 12 would be an example here. So, we're going to just leave the first trivial part off. If you can come up with a way of doing 28 other than 1 times 28, you prove that it's composite. So I think this is 4 times 7. You could write it with parentheses. I'll show you the ways of writing multiplication here. And 39, you might think that's prime, but it's actually, you can break 39 down as to 3 times 13. So besides 1 times 39, 3 times 13, this is definitely a composite number. All right. Composite numbers, when you break them apart, you can eventually, if you keep working on it, end up with just prime numbers as their factors. Let me show you what I'm talking about here. This is what we looked at in example 1. We said 45 could be broken down into the factors of 9 and 5. Now the 5 can't be broken down any further, but this 9 could be 3 times 3. And then once we get to those 3's, we have to stop there. Those are prime numbers. They're in the prime number list. So 3 times 3 times 5 would be 45, and that list only uses prime numbers. To do the same thing on the other example here, 6 times 8, we're going to first split up the 6 as 2 times 3, and then we're going to split up that 8 into 2 times 4, and the 4 itself can be split up into 2 times 2. So if I circle the kind of the ends of these, there's your prime numbers. I'm going to put all the 2's in front, and I think I'm counting 4 of them. 48 would be factored into 2 times 2 times 2 times 2 times 3. And let's make sure we're right. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 3 does give 48. Notice that all of these are prime numbers in this box over here. So we have all prime numbers multiplied by each other. Those are all prime factors. Okay, there's a couple ways to break a number down into its prime factors. I'm going to show you 2 ways, and you can choose between the 2. The first way I call the factor tree. It's more like the bottom, the roots of the tree when you're done. You first break apart the number into however you know how to do it. Other than 1 times 63, you don't want to do that. So I'm pretty sure this one is 9 times 7. You don't have to start it the same way I do, but you should get to the same result regardless. 9 times 7, you could actually do 3 times 21, but let's keep going with what we got here. Now, 7 is prime, so you circle it. But the 9 breaks down, and it's 3 times 3. And because these are primes, you circle them, and now you write this as 3 times 3 times 7. You also want to then write it with exponents. 3 times 3, you're going to say that's 3 to the second power times 7. We're going to do the same with the 80. If you'll think about how to break apart 80, you might not come up with the same pair that I do. I'll give you some options. You could do 4 times 20. I'm going to do 8 times 10. But neither of those is prime, so I have to keep working on it. This one's 2 times 4, and I've got at least one prime number figured out. The 4 is composite, so I can keep going, in other words. So that's 2 times 2, and those are prime. And then the 10 breaks down into 2 times 5, and both of those are prime. So if you look at count the 2's and the 5, there's 4 of the 2's. And times 5. Now we're going to make sure this works before we go on. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 5 is 80. Yeah, we got the right numbers here. And the last thing we're going to do here is write this in exponent style. It's 2 to the 4th power times 5. And there's your prime factorization. using the tree method, and these look more like roots to me than maybe leaves or anything like that. So this is like a tree root system and kind of the visualization here. Okay, that's one way to do it. And the other way to do it, I call this one the line and primes method. So I've got the line, now let's do the primes. You start with your number on the right side, 80. Hang on, let me get the right tool, 80. Now, once you've got that, you're going to divide it by the first, you're going to try to divide it by the smallest prime number, which is 2. If that doesn't work, you move to the next smallest prime number, 3. And you can consult the list we had earlier. And you keep trying to divide it by 3 until you can no longer do that. And then you switch to 5 and bleed that one dry. So here we go. 80 divided by 2 is 40. Divide 40 by 2 and you get 20. And we keep going. Divide 20 by 2 and you get 10. Divide 10 by 2 and you get 5. And here's the first time we can't divide by 2. So I look at it and say, well, 5 doesn't divide by 2. Move on to 3. Does 5 divide by 3? And the answer is an emphatic no. Does 5 divide by the next prime number, which is 5 itself? Yep, there you go. And 5 does divide by 5, and you get a 1. As soon as you get a 1 there, you know you've gone far enough. You've got the answer on the left-hand side. It's going to be 2 times 2 times 2 times 2 times 5. That is the same answer we got earlier. You can compare. It's going to be 2 to the 4th power times 5. That's the prime factorization of 80. And it is the same answer we got when we did it the other way. Okay, so here's another example. We're going to break apart 120 into just prime numbers. You start with 120, and you're going to use 2 until you can no longer use 2. Divided by 2, divided by 2. Divide that by 2, and we can no longer divide it by 2, so you move to 3 if possible. And yes, 15 does divide by 3, gives you 5. And when you get down to this point, you're going, well, 5 does not divide by 3, so you have to move on to the next number, 5. And you get 1 here, which is an indication you're going to stop. So we have 2 to the 3rd times 3 times 5. And let's make sure this gives 120. 2 times 2 is 4. 4 times 2 is 8. 8 times 3 is 24. 24 times 5 is 120. So we've got the right answer here. All right, let's write it out in exponent format. There are 2 to the 3rd to start with, and then times the 3 and times the 5. And there's your prime factorization of 120. Okay, we're going to pick up in the next video, and that's where I'll teach you to simplify fractions. And they're going to break things into factors, so that's why we had this presentation. I'll see you in video number 2 for this section.